Hello, this is Dinesh. Today we are going to give a seminar about artificial intelligence and mostly on real-time or learning real-time A-star algorithms. My name is Dinesh Anavoina, and I have my classmates here, Sai Gogineni and Tiana Velkoska. Tiana will start with the presentation, then Sai will take the initiation on the second paper, and I will conclude the seminar. Yeah, Tiana, you can take her.
Okay, let's go to the second slide. So I will do the present. I will talk more about the KNN, LR, TA, S simple sub goaling for real-time search. Can go next. First, I will discuss the algorithm in general, DLRTA. Then we will talk more about sub-goal database construction. Then I will talk about runtime search and the issues of runtime search. And in the end, I will mention the empirical evaluation. Let's start with the algorithm. So DLRTA algorithm is the first real-time heuristic searching algorithm. The algorithm is used by suited agents in applications that require the amount of planning per action to be construct bounded regardless of the problem size. The algorithm attempts to eliminate learning by automatically selecting sub-goals. The algorithm analyzes a state space and computes a database of sub-goals that are then used at runtime. The algorithm is well composed for video games. It also has a substantial memory requirement and a complex pre-processing module. The algorithm is based on the idea of k nearest neighbors. So the algorithm builds a database of sub-goals instead of like what every other algorithm does, or analyzes a map and builds a click-based abstraction. Okay, we can go to the next slide. So the motive of the algorithm is to retain the excellent performance while simplifying the algorithm and relaxing memory requirements. A big rule here is in the memory consumption part of the algorithm is the sub-goal database. So the algorithm works in a process that a grid-based map is covered to a graph, which then is abstracted to the every click of the original state of the original states become a single abstraction state. Then a grounded level state is chosen as a representative for the abstraction state. Then in the end, the representatives are marked with small white circles. After the separation of the map into regions, the algorithm considers all parts of all pairs of abstract states. For each 2 points, the algorithm finds the optimal path between grounded level representatives of the two abstract states. After that, it trades the path from the start representative and it marks the ground level state where the path enters the next region. Okay, we can go to the next one. So since the computing of the sub-goal for every pair of state is interactable for any non-trivial map, instead of the agent looking up its exact goal, he will generalize from available records. So the mechanism for this generalization is that k nearest neighbors, which means finding k closest cases to the problem at hand, combining their pre-computed answers and using the combination of the solution. The mechanism works in the way that first we set K to be 1, then whenever the agent is in state S start and is going to S goal, it scans the sub-goal database and it finds the most similar record. In order, in other words, we can also define it as the sum of heuristic distance between the S start and the S prime start, and between S goal and S prime goal. Then, when the agent locates the database record, most similar to its current situation, it sets the sub-goal to S prime sub-goal from the records as its own sub-goal, and it persists over using the standard LRTA algorithm. Okay, can go to the next one. So let's see some issues here. There are as there are so many pros, we can see some cons to this mechanism. Some of them are, for example, the goal global is hill climbing reachable for the agent current state. So the agent might still select a sub goal leading it away from the goal. And the second one is the sub goal, S sub goal, is not necessarily a hill climbing reachable from S start by construction, and as a result, the agent might run out of obstacles that are trying to reach it. Then we can see the third issue is connected with appearance of possible cycles. Or to explain this better, the agent reaches its chosen sub-goals and then sets the next goal, which brings it back. However, after reaching the sub-goal, it might end up selecting S prime sub-goals instead of just S sub-goals. And then the fourth one, the fourth problem is ignores the obstacle which can cause the most similar record to end up being on the other side of the obstacle. And furthermore, this can cause the agent to spend a lot of time working its way around those obstacles. Okay, can go on the next one. So there are like 8 maps that are used from popular video games. And as we can see, like on these maps are shown the sizes from 150 times 141 to 243 times 274 cells. On each map, we have 128 different pathfinding problem instances with the start and the goal location that are chosen randomly. And each data point is in average of 1,024 different pathfinding searches. And also, like from the picture, we can see the results or like the testing results, like of the LRTA algorithm, which is like with level L of 3567, which is on the second picture. And then we can compare it with the KNN LRTA sub-goal database sizes, which is like 1,000, 5,000, and 10,000. Okay, Sai and Dinesh will continue the presentation now.
Yeah, hi. So I'll take over from here. So from here, I'm going to explain about the learning real-time A-star path planner for UAV, that is unmanned air vehicles target sensing. So in this paper, we are going to talk about so we are going to introduce what is path planning and UAV, and after that we are going to cover the topics like coupling between path segments, proper utilization of sensor footprint, and the required capabilities for effective path planning from UAV, and discrete step paths, and LRTA research. So me and Dinesh are going to explain about these topics in this paper. We can go to next slide, Dinesh. The next one, it is just an overview, right? So the next slide is introduction to path planning and UAV. So path planning is nothing but setting a path or map to reach the goal position in the shortest duration or without any obstacles. And it is one of the most essential activity in autonomous aircrafts or UAV or any unmanned air vehicles or autonomous vehicles such as drones or any other autonomous things. This path planning process includes aircraft movements as well as the movement of sensor footprint in the specified direction. For example, if we take a map of surroundings I mean, this path planning majorly requires a map of surroundings such as environment and a start and ending position, like target position where we have to reach the goal. So some of the examples for these are like grid maps, state spaces, and topological road maps that we generally see in real life. And this path planning problem is it's okay. This path planning problem is particularly challenging in autonomous fixed wing aircraft because of the restrictions that dynamic aircrafts have, such as I mean, the turning radius should be as minimal as possible in aircrafts, and the other downward looking sensor footprint is also a major concern in aircrafts. And so the next is on path planning for sensing closely spaced vehicles with sensor footprint. As shown in the figure 1, so the main objective of this research is to provide a path planning technique for detecting group of objects that exploit sensor footprints within the aircrafts that is having dynamic restrictions. So if we see in figure 1, our goal is to reduce the time it would take to reach the three targets that are shown in the figure in the white boxes. So there are some technical challenges to achieve this, like the three major technical challenges that we found in here are coupling path between these segments, and utilization of sensor footprint, and determination of viewing order of targets. So if we come to the first challenge, that is coupling between these path segments. So planning path segments that are optimal from one location to another is I mean, one of the most used strategies for path planning. So how to proceed if we have multiple targets? Like if we see in the figure, we have multiple targets like target 1, target 2, and target 3. If we have multiple targets, then the strategy would be like determining the best path from starting position. Like if we see in the figure 5000 is the starting position. So from here we will reach the target 1, first target. And after that, from target 1 we will go to second target, and from second target we will go to target 3, and so on. So if we have multiple, we will continue in the same way. And this strategy works well even if we have multiple targets placed widely relative to the vehicle's turning capabilities, as long as it is ideal in the specified order. So if shown in figure 2a, I mean, it is bad optical path compared to the figure 2b. Like if we compare the distance, figure B has lesser distance compared to figure 1. So I mean, we should follow the pattern used in figure B to get optimal path instead of getting a bad outcome. So, and the other challenge is like proper utilization of sensor footprint. So mostly, I mean, in unmanned air vehicles, we see most of the sensors like LiDAR or UO video or SAR. So these kind of sensors are mostly used to capture the downward looking or downward environment from the air, from these UAVs. So here, as we can see in the figure 3 shows point to point segment in this path planning approach. Like these paths are drawn directly from, I mean the starting position to the goal node, from this blue dot to red dot. So, and as shown in figure 3b, it is using the benefit of sensor footprint for if the targets are placed in closely spaced targets. Since the viewing target of does not need flying directly over it, most of the path planners directly fly over constraints, and they do not take advantage. They are not taking the advantage of sensor footprints that these UAV drones or any other UAV vehicle is carrying. So we can go to next slide. So these are the required capabilities for effective path planning from any unmanned air vehicle. So it should be like planning optimal paths from multiple targets and efficient utilization of sensor footprint. Efficient utilization of sensor footprint in the sense making use of sensor footprints to see the target, to see the targets, so that we can eliminate the need to fly directly over them, and finding the optimal viewing angle of the targets, like specifying the scanning order of the targets, and this will result in reducing the length of pathways, so that we can reach the destination in less time. Yeah, and the next is LRT A-star. So learning real-time A-star search, path planner, and RRT. RRT is nothing but rapidly exploring random trees, and MILP, mixed integer linear programming. So these are some of the algorithms that we use for getting success scenarios in UAV applications. So a path planner meeting technical requirements of optimal paths can be developed by using this LRTA star search. And we mostly use this in path planning for robotic systems, and constructing a tree of nodes by randomly selecting the points in such these are called RRTs. So majority of these methods are created to tackle the circumstances in which the goal is to design a path between the starting position and the target. So mostly we use these for aviation applications. This mixed integer linear programming is mostly used in case of aviation applications like aircraft wings and all. So yeah, we will go to next slide, where we will talk more about discrete step paths. So discrete step path is nothing but it can be determined by it is mostly determined by the prior data that we have, that is based on the vehicle speed and the direction of the track in which the vehicle is moving. So it makes use of all the vehicle sensors to reach the vehicles, to meet the constraints of vehicles dynamic boundaries. So if we see in this figure, the primitive turn, that straight segment assembles from A to C, there are some flyable paths which we have from the function p of x comma y comma psi. So the efficient path algorithm should develop a path that is free of endpoints or headings, and it will be utilizing all the vehicle sensors and sticks to the vehicle's dynamic limitations. So which are made up of simple turn and straight segments to form a flyable path. So rather than moving from point A to B, a set of path objectives such as recognizing collection of targets determines by which primitive we will employ each step, so that the optimal path can be can be determined by using this function. So here x and y indicates the vehicle inertial position and heading degrees in the north, and this xi indicates the direction of travel in which the vehicle is moving. So from here, Dinesh is going to explain about the LRTA research and so on. Yeah.
Yeah, thanks, Sai. This real-time A-star research algorithm is nothing but more as a A-star search algorithm. Conceptually, both are same, but it's kind of an advanced version which can be used in real time. So this learning real-time search, A-star algorithm is more of finding an optimal path for us whenever we use in real time. For example, we talked about maps, for finding an easy path for navigation purpose kind of thing. So that's where this comes into picture, and it finds an optimal path for sure. It takes all the optimal, possible solutions and finds the optimal path, but it takes some time. It's not that speed, but it gives the solution. So the search function is FC equals to KC plus HC. KC is nothing but a heuristic estimate, and the HC is cost of moving. So it all depends on how many branches we have. How many ways, and the distance between the towns and alls. Those all comes under consideration. These are some of the criteria or requirements we can call to determine the optimal path. Initial heuristic search. This here usually will consider the farthest target to calculate the optimal path, because we should take the initial node and the end node to calculate the path between the destination and the starting point. And this terminating conditions, I will talk about this in next slide. I'll give more information in there. Now, branch conditions. Branch conditions are nothing but it's more of a memory management. So storing the information of the path size or the cost values and all. So branch conditions will take care of that. In a tree-based search, basically, it all based on branch size and all. And path tree size is more of it take care of conditions, switch conditions or while conditions or if else condition. Because we cannot go backtracking on this particular algorithm, this path tree size that decreases the memory size and everything, because it eliminates some of the wrong directions. If you're going left to reach our destination, another left will be downgrading side if the right direction is more of an accurate one. So it will eliminate such instances to reach the optimal path in an easy way. And the other one is step size selection. So based on our initial feasible path and length, it will take the fixed size to maximize the speed and the tree depth to determine the optimal path. And coming to the termination conditions that we discussed earlier in the slide. Basically, there are two extreme conditions to find out the optimal path. One is it runs until heuristic change is 0. Until the end, it should find optimal path. And but it can be lengthy. It will find the solution, but it can be lengthy, and it requires a significant amount of running time. So that's one of the extreme cases. And other one is it takes a maximum time to get the optimal solution. It may not produce the optimal solution that we are looking for, but it will still keep on searching for optimal solution for us. Here, these two algorithms were trying to combine these two major drawbacks into a single one to produce easy path for us, because they found this no improvement learning real-time algorithm, A-star algorithm, I would say, because combining these two drawbacks, they're terminating the longest paths to find the closest one. Or if suppose we discussed in previous slide about removing left turns or right turns, right? So here this will take care of that. If the path is not optimal, then terminate the path, so they can move on to other path. So that way they'll find out the optimal solution. And testing and comparison. There are few experiments were done using these two algorithms. Like, they made about 2000 target situations using this 2RT and 2RT globe for both the algorithms, learning real-time A-star algorithm and no improvement real-time A-star algorithms. They both took discrete steps to find the optimal path, and they worked on three algorithms, basically three such algorithms, to find the running time, closest running time and optimal path to improve the performance and all. And coming to the next one, it's kind of validating the tests, how they validate the tests using this real-time A-star search. And they also used, they compared this search to brute force global search we learned in our previous classes. So yeah, this learning real-time A-star search produced best results based on these three criteria, path length and running time and differing number of targets. So as we know, what is path length and the size. Running time is nothing but the distance between the two nodes. Sai was talking about targets, right? Target 1, target 2, target 3. So this path length and running time, it's more of the distance between those targets, and the differing number of targets, as we were saying. Based on the number of targets, they'll take the size, path length, and everything. So overall, in conclusion, they both are excellent algorithms. They both produce optimal paths in their own way, but there's no improvement. Real-time search algorithm produced better results based on the experiments, and it's more of taking drawbacks from one algorithm and improving the other one, so that they can overcome the problems and produce nearest optimal paths as easy as they can. So that's all about this presentation. These are some of the references that we've gone through to make this presentation. Thank you, everyone, once again. We are closing up this presentation.